This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
The IUPAC that you're with, just as a reminder, with IUPAC you find the functional group, then you find the parent hydrocarbon, and then you look at the substituents. You put them in the opposite order, though, of substituents, parent hydrocarbon, and functional group ending. When you number, you give the lowest number possible. The carbon directly attached to the functional group. If there's a tie or no functional group, then you go with a substituent. So the first one is propan-2-ol, and then the common name is isopropyl alcohol. Any questions? Remember that with a common name, that it's only propyl if you have the 3 carbons in a row and it's attached to the end carbon. So since it's on the middle, that's an iso. B is 1-bromo-2-methylpropane. And then the common name is isobutyl bromide. Any issues? Don't forget to go back over your common name structures if they're back in the ratty part of your dustbin in your brain. Okay, C, N-ethyl, 2-methyl, propan-2-amine. You do have to put a number for the functional group because it could have been attached to carbon 1 for all you know. And then the common name, the nitrogen is the basis that you're building off of, and you say what's attached to it. That's a tert-butyl ethylamine. Am I going too fast? Too slow? Too much? Okay, D. 3-bromopropyne, and if you put 3-bromoprop-1-ine, I will accept that too, that's fine. You're giving the numbering priority to the functional group though, so that's why it's not a 1-bromo. And then propargyl bromide, your favorite. E5-methyl-hept-3-ine. Giving the lowest number possible to the functional group. You don't care what that does to this numbering for the substituent. And then the common name, I know you hate this one, that's an acetylene group, and you say what's attached to it. Sec-butyl ethyl acetylene. F is very similar to D, except it's a double bond, so it's an -ene ending. And because it's a double bond, it's an allyl group rather than a propargyl. And I think that's all the farther I went. So we'll check the rest of them on Monday, I guess. So I'm not taking up a lot of class time drawing things out because I want to show you something with resonance today. The rest of your homework, page 44. A has resonance, that boxed in area. You have 4 in a row that have p orbitals that could overlap. B also has resonance because when you count the non-bonded electron pair in the oxygen, that makes it 3 atoms in a row that fit the criteria. C does not. You do have a p orbital for the radical and for the pi bonds, but it's interrupted by an atom that doesn't have p orbitals. So although there are 3, you don't have 3 in a row so that you could shuttle electrons around. Then you would have. Yeah, if I had the radical instead on here, so that you had that, then that would have resonance. D has resonance. The whole thing has resonance. And then E, if you didn't get this right, I understand. When I was looking at this last night, I realized we hadn't quite gotten to that in the lecture, and so you might have seen 3 atoms in a row that have pi bonds and said that has resonance. Fair enough, but this doesn't technically have resonance because if the two double bonds are right next to each other. This set of p orbitals is fine, but you can't line this p orbital up with them because it has to overlap with another p orbital, and this p orbital can't be in the same place. So, yeah.
They can't occupy the same area.
Yeah, so you can't line up all three orbitals all in a row so that you could shuttle electrons around, because that third orbital can't line up with the other two because it has to line up with the orbital that's coming perpendicular.
So if we were to say that the third carbon was to have a carbocation, would it still have resonance?
Then it would have resonance because you don't have a conflict. That carbocation could line up with a p orbital. It doesn't have to line up with something else.
Yeah.
Yeah, this has a requirement to line up with another p orbital to make that double bond, but it can't line up with this p orbital because this is, you've got to do a side-to-side overlap of two p orbitals to make that pi bond. So it has to line up perpendicular. And the idea of resonance is that you're lining up all the orbitals with each other so that electrons can flow through that whole system. So it doesn't work if you have one twisted off 90 degrees. You couldn't have the electrons jump. So sorry about that one. I think the rest of them were straightforward if I remember correctly. F, you can't have resonance there because it's interrupted. So you don't have three or more. G does have resonance through that area I boxed in. H has resonance through the whole thing. I does not. You actually have two interruptions there, but you get the idea. You don't have three in a row. And that's all of them. Do you feel pretty confident about being able to recognize resonance? Okay, then we're going to take the next step today of helping you figure out where the electrons go within a resonance system. And if we're really super lucky, then I can show you how to apply that to a reaction. But one thing at a time. Wow, what's my deal this morning? Okay, so that's what we already did. So on page 4, what do you mean low battery? I can't have a low battery. I need you. Okay, hopefully it'll stick around for a while. On page 5, this was where I hadn't quite gotten yet on the lecture yesterday that might be helpful to you. The first idea is if something has a triple bond, only one pi bond can line up in a resonance system. That's because the other pi bond has to be perpendicular. So what this is showing you is you'd have resonance. You'd have resonance still here because you have a pi bond and a carbocation. That's fine, but only one of the p orbitals will line up with that. The other one can't occupy the same space. It's kind of set off. So it's always only one pi bond that could be part of a p orbital. Of a resonance system. And then the other one is adjacent orbitals can't be a resonance system because only one set would line up. So you can't count those three as all being part of resonance. The double bonds adjacent to each other, that's called an allene, and it has special reactivity and everything. If you took an advanced organic chemistry class, then you'd go through the reactions that would undergo, but we're not going to be doing anything with that. So the pattern that you're always looking for to determine that something has resonance is double bond, single bond, double bond, single bond, because then you have all the p orbitals can line up with each other. I'm sorry, this is such a bunch of lame drawings. I also have them drawn out like with a computer program in the textbook, and although they aren't fantastic, They're better than this, so you can look at that. Maybe you remember from Gen Chem, and don't answer that, but when you have p orbitals, they have to be on the x, y, and z plane. Yeah, so because you're getting electrons away from each other. So this isn't going to affect you very much for being able to work with the stuff you've got to work with in this class. I just wanted to make sure you saw that. Anyway, the structural feature required for a resonance system, if you have multiple pi bonds, would be the double, single, double, single, double, single, that pattern. And that's because each double bond then would have the two p orbitals overlapping side to side. And then you have your single bond here, and then you got the next set of p orbitals. But now since you have a whole series of p orbitals, then these can also overlap with each other, if you have that. So although there's no difference here in the overlap, I was just trying to match it up to this drawing up here so you could see that's where the original double bond is here, that's where the original double bond is here. But oh look, you can overlap this too. So when you're working a problem and you see that structure, you are thinking of resonance as being a stabilization feature as part of the reaction. That's known as conjugated double bonds when they're separated by a single bond, by one single bond like that. So you'll hear that phrase quite often. And they're isolated if you have two or more single bonds, and then that means that you have an interruption in the resonance system, and so each double bond behaves independently. There is no resonance. Everything's running out of power. Okay, so that was a lot of words, but once again, just boiling it down, you're looking for double, single, double, single, double, single, double, single. Okay, all right. So now I've got to show you how do you visualize where the electrons are going. In general chemistry, you learned about resonance and then promptly forgot it because we didn't do a lot with it, to be fair. And I told you in general chemistry, resonance is where you can draw two or more structures that have equally good formal charges, and so you can't, the molecule can't decide, and so it's kind of doing an average of those. That's true, but it's also occurring because you have the p orbitals overlapping, and so the electrons can move through that system. And when you draw resonance contributors, you're showing, well, the electrons can be sort of here and over here, but the actual molecule isn't this or it isn't this. It's that it's averaging them out. The actual molecule, when you draw resonance contributors, it's your best attempt at describing the features within the molecule, but the actual molecule is a blend of those. I explained it to you in general chemistry as if someone had red-green color blindness and they said, what does green look like? And you said, well, it's kind of yellow and kind of blue, and then if you kind of picture those kind of going together, that's green. And that's what we're doing here. We're saying, well, this is yellow and this is blue, and now kind of merge it together, and then you get the actual molecule. When you're working problems, you can do it either way, where you're showing the individual resonance contributors and working with them, or you can work with the blended molecule, and I'll show you how to do both. But anyway, if you're going to draw resonance contributors, first you want to box in the resonance area. I think that you'll want to do that because then it will keep you from trying to move electrons outside of that region, even if it's tempting for you to, because, oh, look, there's a tertiary carbon, I'm going for that one, you know, and well, maybe you can't do that. So this will keep you within that area. There is a lot of theory that goes with why these are the two structures that you're blending together. It mostly involves constructive interference and destructive interference and electron wave patterns and buzz, 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 blah, blah, blah. And that's fine, but I think that what's more important is that you can come up with these structures. So here's your simpleton, like this is me thinking, you know, kind of idea. If you were going to get electrons to this, you can't just unplug them from here and stretch them out over to here, right? You'd have to unplug it here and swivel it over and plug it in there. Okay, so when you do that and flip it over, now you're taking the electrons away from this carbon and you got the carbocation there. So when you're drawing these out, you're thinking the same way that you were when you were doing reactions. Negatively charged electrons go towards the positive. So the electrons are flowing towards the carbocation. Or they're going to flow away from negatively charged areas. Because of that, neither carbon is a full-out carbocation because electrons are kind of being shared with both of them. And since you don't have a regular carbocation anywhere, that's why it's going to be so much more stable than if you just had a tertiary carbocation even, usually. After I show you how all of this works, I'm going to boil it down to a pattern for you. I used to be all about having you show with the arrows where the electrons are going within the resonance system. I think it's still important for you to be able to show how reactions happen, but I've decided that the most important thing you need to be able to do is figure out what the resonance contributors are. So I'll show you the pattern for being able to decide that. And hopefully it'll be a little clearer for you than all these arrows going everywhere. Okay, with radicals, you have the same thing. It's just that electrons are flowing towards the electron deficient radical, but you only need one of the two electrons from the pi bond. So when this matches up, you've got your new pi bond over here. And since you only use one of the two electrons, the other one stays behind on this carbon. Okay? Okay, so you can get out your molecular model kits when you get home. And for instance, it's going to be hard to do radicals because it's hard to split the bonds. But you can picture if you build one of these kinds of molecules and you unplug something here and then plug it in into a hole over here, you got a hole here now. You know, so you can kind of start to see how the bonds could be moved around to make the resonance contributors. And let's see. What do you notice about the pattern if you're comparing this resonance contributor to this one within that area?
What do we notice about the pattern? Just that it goes back and forth between the two.
Okay, but how? What do you notice about the pattern for instance, the carbocation or radical? Yeah, it fortunately ended up on the tertiary this time, but that's not why I put it on the tertiary.
Is it you just flip it pretty much the opposite way?
Yeah. Notice that it's always every other. Here, and then it jumps and it's over here.
So
Here,
it jumps two, not
jumps,
one.
jumps two, not one. Okay? The other pattern you'll notice about this is the double bond becomes a single bond, and a single bond becomes a double. Yeah. Double bond becomes a single, single becomes a double.
So it's almost like the middle carbon is like a shape.
That's right. So if you notice that pattern, even if you're struggling with the arrows, you can hopefully draw all the resonance contributors and figure out where the positive charge is appearing or where the radical is that you'd be working with. So what I would suggest is box in the area where resonance can occur. That way you know exactly where you're working. Keep track of valence electrons so you don't get that all messed up. And then work 3 atoms at a time within the resonance area. Because since the non-bonded pair or carbocation or radical or whatever is going to appear every other, that's 3 atoms at a time that you're working. Even if the resonance area has more than that, only do 3 atoms in a section at a time. And I guess the other thing I would tell you is once you start going a certain direction, or work from one edge of the resonance system to the other edge. Make sure that you work the complete resonance area. Sorry, I'll put it back on just a minute. This is why I've decided that it's best to fill this out the night before. You don't have to work around me writing Okay. And if the carbocation starts out in the middle, then work to the one edge and then work the other direction to the other edge. But what I'm saying is you can resonate electrons within that whole system, so do it.
So when it says one edge to another, if there was like 5 in a row, you would still go all the way to the end.
That's right. But you do it 3 atoms at a time. So you might have to do multiple steps to catch all of the resonance contributors. And I'll show you an example of that in a minute.
What if there's resonance that goes in 2 different directions rather than in a line?
So I'll see if we can find an example. Because usually it's just going to go, it might turn a corner the way it's drawn or something, but it's going to go one direction to another. I don't think you can branch electrons off, I guess is what I'm saying.
Kind of skips the middle, goes to the third. That's where it moves.
That's right. So when I had students drawing arrows for coming up with the resonance contributors, then a lot of times I would see this at the bottom, where they're moving everything in one shot and like, okay, here's the resonance system and I'm going from this end to this end, so I'm going to move these at the same time I move these, and they're coming up with only 2 resonance contributors. But if you do it that way, then you miss one of them because you're always working 3 atoms at a time. And so the positive charge is going to be here, and then it'll be here, and then it'll be here. So you should have 3 resonance contributors for that. So the take-home message is working groups of 3 atoms at a time. Just do 3, come up with and draw that structure, and then do the next set of 3 and keep going until you get to the other end. Something that you can do as a double check is to figure out how many resonance contributors you should come up with based on just looking every other and counting. See, so that same example I had up above, I'm showing you that if you drew the 2, but you did a check, it'd be like, oh, I'm missing something here. The reason why it's important to be able to recognize resonance and then be able to draw all the structures is because you notice that the positive charge, for instance, of the carbocation, if it's every other, in the end when you have to resolve it by adding a pair of electrons from something like a bromide, for instance, there are 3 different places that you could put that then. You have to know that so that you can predict all the products that are possible. So that's the reason why I'm having you do this. That was an awful lot of information without a lot of practice or examples. So here, let's do some examples. Skills check 2 on page 9. So I'll show you the first one here, and I'd like you to practice some before we go on. Oh dear, are you going to make it all the way to end of class? Come on. If you see a resonance area, then you want to box that in. Here's 3 in a row, carbocation, pi bond. That's where the resonance could exist. Then you notice that you have a positive charge here within this group of 3. So you're skipping every other. There it is. And that happened because this bond moved up to here. So the single bond becomes a double, and the double bond becomes a single within that group of 3. You're taking this pi bond out away from here and plugging it into here. That's why the carbocation's here. If you're plugging this in here now, that single bond becomes a double bond, and we've taken the electrons away. So the double bond becomes a single. Within that group of three, that's how you come up with the resonance contributor.
If that double bond, the other one that you don't use, if that one was 1 over, then could you use both of them? Would you be able to go both ways?
Yes. If you wanted to draw the actual molecule, then you draw a dashed line where the double bond had alternated and partial positive charges where each of the carbocations was. You kind of blend those together.
So that's just saying that both of those exist, right? The first two.
If you blend both of those together, you get the actual molecule.
Which is the bottom one.
Yes. So it's not like the molecules flipping back and forth, or you have a population that's one and a population that's the other. It's just this is the best way to describe what the actual molecule looks like. It's kind of like it's sort of this and sort of that and kind of put it together. All right, so you got more problems below it. I'd like you to take a crack at coming up with the resonance contributors. I have a lot of things going on in what I've diagrammed out. All I'm putting this up for is to make sure that you see where the resonance area is so that you're boxing in correctly. I'll explain all the other gibberish going on later. Oh yeah, I need more space because I only have 3 of them drawn out. We have to do a 4th one here. Uh-huh.
Because this is a whole connected system. If we share those double bonds, I have positives.
That's right. That's right. So one of the purposes of this practice problem is to help you work when you have more than 3 atoms within the resonance system, to help you learn how to work in groups of 3 at a time, but then keep moving it over. The other purpose of this is to help you see if you've got the instability in the middle of the resonance system, with the contributor that you're given, that you've got to go to one end and then to the other to come up with all of the resonance contributors. So for example, if I go to this end first, I'd be taking this bond out, moving it over, plugging it in here. Then the carbocation is here. This becomes a single bond, and that becomes a double bond. And then that's your contributor. You're just working with those 3 atoms. Then if you're going the other direction, you take this bond, move it over here. So now the positive charge is there. The double becomes a single, the single becomes a double. Everything else stays the same though, as the way it was drawn up here. You're just doing 3 at a time. Because this would be every other, it means that you would also draw a contributor by moving this over and having the positive charge here. I ran out of room. I'm trying to write big enough that you can see. So I made a note to the editor that I need more space there. So sorry about that, but there would be a 4th contributor. If you didn't want to draw out all the contributors, then the alternate way that you could draw the actual molecule is by thinking, well, the positive charge will appear every other, and since it's no longer restricted to one atom, these are all partial positives because it's being shared and distributed. And then the electrons are flowing through this whole system, so you'd have a dashed line going all the way through here. So that's the way that you could draw the actual molecule. This is a whole lot easier, right? So you're probably saying, why don't I just do that? Why didn't she show me that? This is a whole lot easier to figure out what the actual molecule looks like if you're just doing a partial whatever every other, and then just drawing dashed lines everywhere. When you do the reactions, I think that these are going to be easier for you to work with to predict what the product looks like. So that's why I don't know which way is going to work for you better. And so that's why I'm giving you options. All right, the next one is a little bit easier because you only have 5 atoms in the resonance system, and so you're only going to have 2 more contributors beyond what you have showing here. So give that one a try.
Minimize it.
Mm-hmm. Maybe it will be less jubbly to you if you're like highlighting the 3 that you're working with or something. I don't know. Okay. Maybe that's the deal. Okay, so I'm looking at these 3 atoms now. Yeah. And so now this is going to be every other, so this goes to here. The double becomes a single, single becomes double. Yep, so just keep working your way along the... Uh-huh. So everything stays the same from the step before, except for that group of 3 that you're looking at. Just do 3 at a time.
Your carbo, the
Radical?
on the bottom,
Yeah. It's right there.
like on the bottom of the C.
Yeah. So what I did was this set of 3 atoms first. The radical went every other, so it moved from here to here. Double became a single, single became a double. Now I got the radical here, but I've got to keep working the same direction to get to the other edge of the box. So now I'm going to look at this set of 3. Radical goes to here, single becomes double, double becomes single. And then if I had one more, I'd take this one, do the next group of 3. Everything else stays the same. Change within that set.
What's the point of changing it?
Because the actual molecule is going to have a little bit of radical character here, here, and here. So if you were reacting this with HBr, for instance, the hydrogen would end up here, here, and here in 3 different products. You'd form 3 different products with the hydrogens in alternate places. And so you have to be able to track where the reaction could occur, all your possibilities. So I think that you need a lot of practice. So I'll give you some homework where you're drawing out resonance contributors. Now, naming. Stereochemistry. Somebody asked me if you're going to get a review for the final exam, and I can put together a review for you, but if you notice that these practice problems at the end are pretty much a review of all the chapters up to date, so you'll get a lot of review here. Aha! Page 49. Page 49, write all the resonance contributors for each of the following. You don't have to worry about the major, minor, or contribute equally, but if you wanted to, if you're just kind of bored this weekend, if you have different resonance contributors, one has a carbocation on a tertiary carbon, one is on a secondary carbon, one is on a primary carbon, the tertiary is the major because that's the most stable. You're just looking at stability, just the way you've been doing before. If they were all secondary, then they all contribute equally. Anyway, take a crack at that and see if you can come up with all the resonance contributors. And as I said before, one thing that might be really helpful for you is to figure out how many you should draw by going every other. So for example, the first one here, you should have a positive charge here, here, and here. So you should draw 3 more contributors. Okay? All right.